Hi, and welcome, and thank you all for being here just before beer o'clock. I know it's a Friday. I know it's hard to beat today. I'm going to talk a bit about databases. I know it's not what people generally associate with SRE, but they are still there. It's still a thing we still need to keep state because there is an inherent paradox in the cloud. We have applications on one side. We have Kubernetes, we have platform as a service, we have Lambda, we have step functions, we have a lot of things that will scale up, scale out, and allow us to run applications, scale out horizontally, multi-zone, multi-region. It's easy because it's inherently stateless. But at some point, you need to keep state. You want the data to save, you want to store it, you want to retrieve it a few days later. You want the ledgers in the bank, you want the user cookies, you want sessions in your web app. You want the different things that need to be saved. Just fell over. And that's where things start to break because we had databases. Databases are not a new thing. We have them from way back then, from 1970s when IBM and started creating databases on mainframe, but they were inherently built to scale up on a single server and support monolithic systems that are running on-prem. And this new cloud thing that you may have heard about presented new challenges, scaling challenges, presenting network topology challenges, present challenges running multi-region, multi-geography, different continents that all need to support. I'm Harel Safra. I'm a senior manager of data platforms at Riskified. Riskified is a fraud detection company in the e-commerce state. And my team is one of two platform teams in the data domain. My team runs databases, various different kinds of databases to support the different systems. Questions are encouraged, but if not burning, let's keep it to the end. And who has touched or managed a database? Okay, nice. Who's only been on the application side and just what's the key? Don't touch that like it's a skunk. Yes. Thank you for your honesty. So, what do we need to consider when we're choosing a database or think about storing the data in the cloud and having state? The first of all is that a database is not a database. There are various different kinds of databases, very different kinds of data models that support our systems, and there are more. Okay, I simply didn't have enough space on the slide. But we have different kind of data models. Each one of them supports different kind of systems, different kind of access patterns, and allow you to do different things with them. We start with a relational one, which is a standard SQL that we all had in the past. Relational for tables, okay, spreadsheets, but for systems. These tables can be joined, can be queried, deleted, updated. And the most important thing and the cornerstone of most SQL databases, or at least the traditional SQL databases, is that they have transactions. Transactions allow you to make a single change to multiple records that will all persist or all fail. So if you take, for example, a bank where you want to move money from one account to another, you want to deduct the money from one account, you want to add the money to a different account, and you want both operations to either succeed or fail. But you don't want to deduct money and not put it somewhere else because then you just lose money and it's frowned upon. Yeah. We have key value databases, which are inherently accessed by the key, by the primary key, or they have different names. Mostly a key that allows you to access a value. Most of the databases will allow secondary index access, not only by the primary key, but it's inherently costlier. It means it have various indexes that index into the primary index and then index back into the value. If you find yourself using secondary index, don't probably use a key value database. The good thing is they are very simple, very easy to understand. Key value, it's like a hash table, but persisted somewhere else. We have distributed SQL, which is the new kind of SQL. There are not a lot of databases that support this model. We have CockroachDB, YugaDB, Aurora DSQL was announced last year. These are scale-out databases that will try to still have the same kind of primitives of transaction, atomicity, and while being horizontally shardable. We have columnar stores for data warehouses, for analytical queries. We have graph databases for questions like, who are my neighbors? What orders match that order which was fraudulent? And we can learn from that and traverse the graph to see other similar properties. So if you find yourself interested in the connections between a data point, a graph database is probably your go-to choice. Also, a big consideration is between database as a service and self-hosted. Obviously, not unique to the database area here. When you self-host a system, it's more flexible. You can do more things with it. You can have more integrations point into the system and allow you to better work and better tune a system. Some of the cases you can have open source products and save a bit on license costs, but it's more complex. It has more operational burden, and then just buying a service. Buying a service will allow you to scale easier and allow you to not necessarily build all the knowledge that's needed to support this database. It doesn't mean you don't need any kind of knowledge, because all database as a service that I know at least requires some kind of involvement. You either create users, or you create indexes, or you need to tune the access. But you do need to do something with them. But it's less. You don't need to back up usually. You don't need to scale. You need to do half of the monitoring, but not all of it. And we're talking about scaling. There are two different kind of scale. You can either scale up, meaning running the same kind of process on bigger servers. And that's usually what we had in the past, scaling up the server, the memory around, CPU around, buy a bigger server, resize the server, and it does work up until a limit. And the limit is usually where the process itself lock each other, either by locking or by simply trying to access the same memory area at the same time. The other type of scaling is horizontal scaling, where you have more and more instances of the database. You can have horizontal scaling by having multiple read replicas, and that's the classic one when you have just a single writer, in Postgres, MySQL, for example, and then you replicate the data over to read replicas. So you can have more read capacity, but it's still bounded by it. Or you can have the database sharded out completely, meaning each part of the database is managed by a different server, and the key space either is split up into different regions that are managed by different servers. There can be a hash. It's usually a hash on some kind of primary key that allows you to split the data between different servers and allow more servers to share the same workload. Reliability is obviously important, and we need to keep the data safe. We need to keep the data secure and available. And the way we usually do that, and the way most servers do that, is by having some kind of redundancy. If you want to, obviously it costs more. But if you need this kind of redundancy, say for a server failure, you need the data replicated somewhere else. And this mixes and matches, and you can have different levels of availability for different kinds of failure scenario. The most simple failure scenario is a server crash. And if you just want to guard from a server crash, the simplest way to do that is have the data not on the server. Some servers will have dedicated local storage, which evaporates when the server reboots. Some servers, you can tie your database to run from EBS drives or block devices or NFS, and have the data outside the server. That solves a simple case where the server crashes. The more complex case is where an availability zone crashes. I assume we're all aware of availability zone. Cloud regions are distributed into different availability zones, which are different data centers in the same area, approximately, a few tens of miles between them, but the same area. And data centers and availability zones do crash. It doesn't happen a lot, but it does happen. And the way to guard from this is to have your data replicated to a different availability zone, usually inside the region. You do that because inter-region latency is quite low, so it doesn't cost a lot of latency to replicate the data between different regions, inside the region, between availability zones. And you have a master copy and you have a replica copy. And when an availability zone crashes, you can switch over to that. And that's the example here. And that's an example that supports both scale up and scale out solutions. Because if it's a scale up solution, you have a single database you need to replicate. You can also do that with scale out solutions But with scale-out solutions, the usual way to do it is spread out your cluster on different availability zones, meaning have servers of the same cluster deployed between different availability zones or different cloud regions or different cloud providers if you're willing to get to have that complexity. And in case an availability zone crashes, if you replicate inside a region, or a region crashes, if you replicate between different regions, theoretically, this should be totally transparent to you. Aside from the lost capacity, because the nodes have just poofed and went away, you can still work with the data because the data is replicated to a different area, either a different data center or a different region altogether. The second part of reliability is that it doesn't always work, because sometimes your database will have software bugs that will corrupt your data. And sometimes attackers will encrypt your data because they want to ransomware you. So they usually encrypt the database. They can encrypt the database. They sometimes take the extra measure of encrypting your backups too. And you want to have a way to recover in case the whole high availability solution failed, either because you planned for a single AZ crash, but the region went away, or because someone deleted the table. Human errors are very much a thing. People do bad things to production and can delete data from the database, and you want to return, and you want to have a guard on that. And here we have an introduction of RPO, which is the return point objective. How much data can I lose? Can I lose a minute's worth of data? Can I lose, because I'm saving clicking for an attribution, it's not that important. Can I lose 24 hours of data? Because it's clickstream and I'm thinking I'm crunching and creating user profiles for tracking. Maybe not, it's not that important. Maybe I can't lose anything because as we're in the bank again. So I have to have every single transaction replicated and copied over, and I can't lose everything. Anything at all. This is a business decision. How much the data is worth is very much a business consideration, and the cost of losing the data and having to recreate it, replay it, rerun it from somewhere. The second concept I'd like to involve is RTO, which is return time objective. How long from the crash do I have to restore? Do I have to have it in minutes, hours, days? And this is also a business decision, and this usually directly incurs downtime. Something bad has happened. A table was deleted from the database. How long do I have to restore it? Because every minute that it's not there, I can't use the system, and I can't return service to our customers. When you're planning a backup strategy, the general rule of thumb is the 3-2-1 rule, which you may have heard about. No. 3 copies of your data. One of them is your production copy, and 2 other copies, at least, on 2 different media types. At least one of them has to be off-site. Why is all that? You have 3 copies because you have a production copy and 2 additional copies in case the production copy is lost, and believe it happens, the first backup is also bad. You want to have 2 different media types for your data. If you store your data in EBSs, have your backup not on EBS snapshots, because an EBS service failure can destruct both your data, your private data, and your backup. So if you're using EBS, for example, as your data, store the backups on S3, on an object store. If you're using an object store, replicate to a different object store, just to have 2 different media types, because failures happen, and sometimes service failures happen in the cloud provider service itself. It does happen, it has happened, it will happen again. Failures always happen. Have a copy offsite. Offsite meaning replicated to a different region. Offsite ideally is offline altogether, either locked with a service that allows just read once, write many, worm. So you can read, but you cannot destruct the copy up until a certain time has passed. Or actually having it on tape and removing it from the system. Why is that good? Because of ransomware. As I said, ransomware criminals will sometimes infiltrate your system, wipe the backups, encrypt the production database, and then you're basically out of luck because you don't have and anything to recover from. If you have an off-site, offline backup that's locked somewhere and can't be touched, you can still recover with that. And after I scared you all to death, there are day-to-day management operations. You have to monitor your database. You have to monitor CPU utilization, IOPS, usage. You have to implement security because your CISO will tell you things like PCI and SOX and SOC 2 and other swear words that all relate to compliance. So you have to have users, you have to have control, you have to have least privilege access to the production. You have to do performance tuning, create indexes if it's a relational database, query optimization. In case of a data warehouse, you need to tune things, you need to changing. You do need to have some kind of knowledge on the database structure itself. And obviously cost. Cost is a big thing. All of us, I assume, we work at companies that want to limit the costs. Reserved instances, commitments will allow you to save on the cloud costs. So how do I choose the right database for my system? You need to start by looking at the data model. What does it look like? Does it look like a big table that needs to be saved? Do I need to allow text-based access? Then I probably use a search engine like OpenSearch or Elasticsearch. Do I need very fast access by key? Redis and in memory. Am I interested in the connections between the data points? A graph will probably work there better. You need to look at the access patterns. Is it an online system? Is it a querying system? Is it a dashboarding system? How much consistency do I need? Do I need to have strict consistency, like in banking? Can I have eventual consistency that will reconcile after half an hour in case of just storing web traffic? How much scale do I need to support? Is it a small one? Do I support hundreds of thousands of users? Do I need to support millions of operations per second? How much throughput does the database need to support? And last but very much not least, what do you know? What kind of in-house knowledge do you have? Are you proficient in running databases in-house? Maybe just adding another database is not that hard. Do you want to abstract it all away or most of it away? And you can choose a service. Does anyone have any kind of example that they want to test against this framework? Any use case that you recently deployed? No. You seem to want to say something. Yeah. Okay, so let's run quickly through an example. Let's say I want to have a dashboard, a user-facing dashboard for my system. I have a system, a theoretical system that processes orders. I want to have a dashboard that will allow my customers to see their orders and slice and dice them and see how much money they spent on my e-commerce website. So the data model could be relational because I want to store orders as they type. But if I would want to have more options for the user, maybe I would want to allow full text search to allow them to search for orders that they created. So a search engine like OpenSearch may fit here better. We need to decide what we have in-house and what we're willing to invest in. It's mostly a querying offline or semi-online type of operation because it's not the orders themselves, but it's reporting on the orders. So we want low enough latency to make the users not frustrated, but it's not single millis or tens of millis latency. You can probably answers in a second or two, which will be fine. Consistency. You don't really need a lot of consistency here because data flows from the system of record, which is the online system, into this reporting system. So it can be eventually consistent. Users are also usually tolerant of some kind of lag when they're talking about dashboards. Scaling, that obviously depends on the amount of users I have that will create, but it's usually lower than the actual production system itself. And in this case, my team does manage Elasticsearch, so we can just implement it on Elasticsearch. But if you had other kinds of, you didn't have this in-house knowledge, you could probably use a service. That's an example of how we can use that. Yeah. 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 It could and could not be because the data model is not necessarily is how the data looks and what do you need to access it and how do you need to query it. It's not necessarily how much queries per second or does my team know about it or is it an online offline operation. If it's not, it doesn't dictate other things. It dictates what kind of. It's usually the question of what I want to do with my data, and not how frequently I want to do it, or what the latency requirements, or how much what team knows. And I'm happy to elaborate. We're just out of time. So as a key takeaway, cloud can make your stateful data even more critical as application pods, application scale up, and just delineate this to a different kind of service. That database, the state, becomes probably more important. There's no best kind of database. As I said, there are different kinds of databases. All of them fit different kinds of constraints, different kinds of criteria that may or may not be relevant in your case. Strategic, the database as a hosted or a self-service solution is something you need to investigate in. How many hours, how much effort do you want to invest in building this kind of the proficiency to support something in house and reap the flexibility that it provides, and versus how much you just want to pay and be done with that. And design for scaling and failure from day one. I can not underestimate it. I have a system in production now that we're kludging together, and we're breaking up the database into different sections at different times, because it wasn't created initially to support this kind of scaling. It is a single read. It's going to be a single endpoint. All reads and writes go to a single place. You cannot it doesn't know how to read from read replicas. It does not know how to scale out. It has a monolithic database, and we are really suffering from that. So if your service is going to scale, try to build that from basically from day one. And now, questions. Any other questions before I return to that point? Okay, so yeah, I do understand what you're saying, but it's not necessarily driven off of that. There are non-functional requirements that relate to what we know and the latency that needs. It's called non-functional, but latency is very much functional. But latency and throughput and how many users we need to support at the same time. And these are not necessarily inherent part of the data model, because the data model is usually how I want to access it. If I want to access it, they do obviously influence one another. If I really must have single millisecond latency for 2 million operations per second, I pretty much have to go for a key value and work with that. But if it's not inherently such a hard limitation from other requirements, then you can choose. If your data looks more connected and you're interested in connections and data points, like a social graph, you build a graph and have the other requirements fit that. If it's more tabular, then probably relational. As I said, there's no one simple solution, and it's sometimes better to just, if you have some kind of database, kludge in the system to work on that database, and not have to build proficiency, which takes a lot of time.